look at the review questions from Chapter 6. The first one, consider the experiment of tossing a pair of fair six-sided dice. Find the probability the sum of the numbers are face-up is at least 9. So we have here, remember, when you're looking at two dice, we have die 1 and die 2. There's 6 options for the first, there's 6 for the second. It means there's 36 combinations altogether. So the probability of this is going to be something out of 36. Go to the data set over here of all the dice, what it looks like. And we want that the sum is at least 9. And you're going to look at the outcomes here and notice that there is a total of 10 different that meet the requirement of being at least 9. So 10 out of 36. And that fraction will actually simplify to 5 out of 18. Looking at number 2, we have a fair spinner with 6 congruent sectors numbered 1 through 6 is spun twice. So spin 1, spin 2. 6 outcomes for spin 1, 6 for spin 2. Again, 36 possible outcomes. What is the probability that the first spin is a 4 or the second spin is an odd number? So this would be probability that first is a 4 or second is odd. In an OR probability, remember it's addition, so we'll do the probability that the first is a 4, add to it the probability the second is an odd, and don't forget to think about if we have to back out any times where the first is a 4 and at the same time the second is odd. Now I'm going to actually pull up the sample space for the dice because it's going to look the same way even though they're dice and not a spinner, and we'll compare and look at that. You're going to notice the dice in the upper right hand corner. Again, because it's a spinner with 6 congruent sectors, I'm assuming the first one we see here would be spinner 1 and spinner 2, so just an easier way to look at it. Of that, there's 2 spins, so 36 options. The first is a 4. You're going to notice I boxed it in the green. That would be 4 out of 36. Have the first being a 4. Plus I'm going to add to it that the second is odd. The second one is odd. You're going to have, in this case, there are going to be 18 out of 36 that would get you that answer. But then you back out all the cases where the first is a 4 and the second is an odd. Those are the blue ones that I circled, and that's 3. When you simplify this fraction, what you're going to get is, get 21 out of 36. You can pull a 3 out of each of it, so 3 out of 21 will leave us with 7, and a 3 out of here would be 12. So the probability is 7/12. Okay. There is a second way you can look at this problem if you don't want to have to look at the entire sample space. Let me just quickly show you how that works. What you could have done is, for the probability of getting a 4 on the first spin would be on a single spinner, you could do it was 1/6. Then you could add to it that the second spin is odd. There are 3 odd numbers on a second spinner, so 3 out of 6. And then you'd have to subtract the cases where they do overlap, and again that's 3 out of 36. If you were to get a common denominator of these fractions and simplify, you'll get 7/12 still. Going into number 3, the question here, how many 4-letter permutations can be made from the letters in the word hospital? If you count this up, there are 8 letters in the word hospital. Permutation means no repeats, and I want 4 letters. You could do 4 spaces. This would be the product of integers, and we could say we are going to choose 8, then 7, 6, and 5, which will give us 1,680. You could also do your calculator. Say you have 8, and you're going to choose 4. So in the calculator, type in 8, and then NPR 4, and you will get the same answer for that one too. So you can do the product of integers or the permutation formula. Number 4 is an extension of this problem. Again, the word hospital has 8 letters in it, but now I want to do a 4-letter permutation where there is no P can be in anything. So a 4-letter permutation. If I can't have a P, that means I only have 7 options for letters now. So I do 7, 6, 5, 4, and that's going to give us 820 or 840. Or you could do 7, choose 4 on your calculator, and get the same answer for that. Number 5 continues with permutation. There's 2 ways you can actually do this formula. You would say it's 10, choose 4. So you have, if you want to imagine 10 slips of paper and a hat, you're going to choose 4. So you're going to make 4 choices. Your first draw in, you have 10 choices. A permutation means you do not put the slip of paper back. There are no repeats. Then you have 9, 8, 7, which is 540. You could also use this formula that says 10 choose 4 would say do 10 factorial divided by 10 minus 4 factorial, which is 10 factorial over 6 factorial. 10 factorial, again, is just 10 to 9 all the way down to 1. 6 is 6 to 5 all the way down to 1. What you're going to be left with, this stuff ends up crossing out if you were to do this method, would be the product method of 10, 9, 8, and 7. So you would get the same answer for that problem. Last thing you could do is in the calculator, again, do 10, choose 4, and you will get the 5,040. Now, if you look at number 6, it says what is meant by 10p4. All they want you to realize is that 10p4 just means this. It means you have 10 things and you're going to choose 4, as we've talked about in the problem. Number 7 is testing your ability to look at this formula right here. This is conditional probability from section 6.6. And what it says is this. A and B are 2 events that in an experiment where the probability of A is 0.5, the probability of A and B is 0.2. Find the probability that B happens given A. The formula for this in the book says this. Remember, it's like a sideways fraction. So what I want to do is find the probability of this on the bottom of my fraction. So put the probability of A on the bottom, which is 0.5. And on the top, you combine the two, and you're going to do the probability of A and B together, which here is just going to be 0.2. And when you simplify this fraction, it's just going to be 2/5, or it's going to be, as a decimal, 0.4, which is going to be the final answer for that. And again, they're just testing your ability to understand conditional probabilities formula. Number 8 says A and B are mutually exclusive. Remember, mutually exclusive means they have nothing in common. Given that probability of A is 0.6 and B is 0.1, find the probability of not A or B happening. What you can do is find the complement of this. The complement of not A or B would be doing this, 1 minus the probability of A or B happening is the same as the probability of not A or B happening. So just remember the probability of A or B. To find that, all we do is probability of A plus the probability of B. And then you would normally subtract out any time probability of A and B happen together. Once we have this answer, we will take it and subtract it from the 1, and we'll get it. So be cautious here. Probability of A is 0.6. Probability of B is 0.1. Now, the probability of A and B happening together, it's impossible because they're mutually exclusive. So this does not exist for the formula. So what we have is 1 minus this number, or 1 minus the 0.7. So the probability of not A or B happening is 0.3. What they want you to get from number 8 is this. The complement. To find the not of something, you can do 1 minus the opposite of that, which is the, here it says not, so here would be without the not, and just think of it backwards. So that might be helpful to think of complements backwards. Number 9 is from section 6.8. It says here, each of the whole numbers from 1 to 8 is written on an index card, and the cards are placed in a bag. A card is drawn from the bag, the numbers recorded, and then put back in the bag. The process is repeated, so there are a total of 6,600 card draws. What is the expected number of times the number 5 will be drawn? The formula to find the expected number was this. It was take the number of experiments done times the probability of that outcome happening. The number in the experiment is 6,600 draws are happening. The probability of drawing a 5 from a bag of 1 to 8 numbers is 1 out of 8 times. You multiply that through and you should expect the card with a 5 to show up 825 times. Number 11 continues on with section 6.8, dealing with the law of large numbers. And here's the incident. It says in 11, and then we'll get to 10, could you decide if the 8 cards are equally likely to be drawn if 5 is drawn 4 times in the first 20 draws? Explain why or why not. So what's happening is they're doing 20 draws. Originally we did 6,600 draws, remember. But in 20 draws, the number 5 actually happened 4 times. So if you do the relative frequency of that, 4 over 20 is 1/5. Now, that is the relative frequency. The probability of actually drawing a 5 is 1 out of 8 times. So the problem is the actual probability is this versus the relative frequency. And what they would say is the sample size of 20 is just not big enough to reach any conclusions. The law of large numbers would say the more that we do this, more we go beyond 20 draws, but closer to the 6,600 draws, for example, that this 1/5 will actually become closer to 1/8. Okay. Now, going back to number 10, if the result of experiment was below, what might we conclude about these 8 index cards? If these outcomes here represent the 6,600 draws, you're going to definitely see something that's sticking out, and it should be about the index card number 5. There's quite a few more of those index cards being drawn, and this would say the law of large numbers has probably kicked in. They've done this experiment many times. We would expect this to happen equally amount of times if they're all likely to happen. Because it's not, we could assume that there's something going on with that index card number 5. Maybe it's a bigger card, maybe it has sharp edges, or makes it for someone to want to grab it. It's just not fair, basically, is what it comes down to. Okay, number 12, a pair of 6-sided dice is rolled. Let A be the event that a 6 is rolled on the first die, and B the event that the sum of the numbers rolled is 10. Are A and B independent events? So we want to remember the test for independence is this. We're going to find the probability of A and then times it by the probability of B. We're then going to compare that to finding the probability of A and B together. So let's go ahead and I'll show you what the probabilities end up being and explain why. If you look at this, you'll notice the probability of event A. Event A is that a 6 is rolled on the first die. There's 1 6 on a die, so it would be 1/6 is the probability. And note it's the probability of A, so that's 1 fraction. This next one wants another fraction, so the probability of B happening, which is the sum of the numbers rolled, is 10. There are 3 scenarios that will give you the sum of the numbers rolled as 10. A 6 and a 4, 4 and a 6, and a 5 and 5. Remember, doubles can't be double counted. You simplify, this fraction becomes 1 over 72. Now the difference is this. When you do this second test right here, notice there's only 1 P. They want 1 probability. They want 1 fraction. So go back to your data set of the 6 die, rolled twice, so 36 outcomes, and count all of them such that the sum, or the 6 is rolled on the first die, and at the same time, the numbers rolled is a 6. Now we know on that there's only 3 outcomes, the 3 of the 36 that we got right here. But at the same time, again, a 6 is on the first die and then the sum is 10. Only 1 outcome works, and it's this. So the fraction is 1 out of 36. These 2 fractions do not equal, therefore these 2 events are considered dependent on each other. It means one does end up impacting the outcome of the other.